differentiated services code point. My name is Keith Edwards. I'm an instructor for Skyline Advanced Technology Services. So let's talk a little bit about differentiated services code point. We do differentiated services code point, or discuss it rather, as part of the concept of quality of service and how we use and implement quality of service tools. Remember, quality of service is about treating some traffic differently than others. One of the historical definitions of quality of service is managed unfairness. With multiple types of traffic going through a network, which have various different requirements, how is the network to recognize one type of traffic versus another in order to treat it better? So what we have to do is to teach the network devices how to recognize one type of traffic versus another. Now, how are we going to do that? There's a thing called the MQC, the Modular QoS Command Line Interface, which gives us commands that allow us to tell Cisco routers and switches how to recognize the different types of traffic. The thing is, the criteria that we use to recognize one particular type of traffic versus another may be rather in depth. So for example, I could say, recognize this source address and layer 4 port when it goes to that destination address and layer 4 port, and treat it thusly. Okay, well, that's a lot of bits and bytes to recognize. So what we do is we follow this concept of classify and mark as close to the edge as possible. That way, we can have the edge device, in this case it's a switch, you see, we could have the edge device do all the high CPU recognition, recognize all these fields, and then we would tell it to mark that data. That way, as that data flows through our network, the criteria the subsequent machines need to look for is far smaller than it is at the edge. So instead of looking at source and destination IP address and source and destination port, I can tell it to look, for example, at 6 bits, 6 little bits in the IP header. Remember, one IP address is 32 bits long, okay? So what I've said is, I'm going to recognize this as close to the edge as possible and mark it so that all the machines it goes through along the way can recognize it much more quickly by looking at, depending on the technology, you're using a 3-bit field, a 1-bit field, or a 6-bit field. All of these are less than even one entire byte. So in this case, we're saying we're going to, at the edge, recognize voice and mark it diffserv code point EF. At the edge, recognize our mission critical data and mark it DSCP 26, which, by the way, is the same thing as AF31, and I'll explain that later. And then as it goes through other routers and other network devices, they don't have to look at a whole bunch of criteria. They look at that one little 6-bit field in the IP header, the differentiated services code point bits. And that's how they recognize data as it passes through the network, and then they can be called upon to treat the different types of data differently. So with policy maps and marking, once we've recognized a type of data, we can tell our routers and switches to mark it, as I was just saying. So we can mark at layer 2 with the cost bits in the VLAN tag. If you were using ATM or frame relay, that's a 1-bit field, the cell loss priority bit or the discard eligibility bit in frame relay. And at layer 3, we have the availability of recking IP precedence, which is the way that was done originally back in the day, and it's only 3 bits out of the toss byte in an IP header, or DSCP, the newer standard, which came around the year 2000, which recognized 6 bits. Or IPv6 also has a type of service field which can recognize diffserv code point as well. For marking, we have a class map for voice, right? And it's matching on costs. That's layer 2 marking in the VLAN tag. It's matching on layer 3 marking And it could even use a tool called NBAR, Network-Based Application Recognition, to recognize the actual protocol. And in the policy map, we can say, I want to mark or remark traffic the way I want to. So even if I were just matching the protocol or matching the data based on the protocol here, I could mark it so that those 6 bits of diff-serve code point could be set and easily recognized throughout the network, so no subsequent machines would have to look at the protocol to recognize this data. And you notice I can set diff-serve code point, and if I'm sending this data out on an Ethernet interface, which would have a VLAN tag, then there's also within the VLAN tag the ability to mark the class of service. Okay, within the VLAN tag. So there's marking at layer 3 and layer 2, and I can do them both if both fields are going to exist on the traffic going out of an interface. I could set IP precedence. That's the old way of doing it. If something is going to a carrier who's using MPLS, well, there's marking built into an MPLS label as well called the experimental bits, and it's 3 bits in size. Just like the cost value is 3 bits in size, as is the IP precedence, 3 bits in size. So again, why am I marking and why am I talking about recognizing layer 2 or marking layer 2 and 3? Well, if I'm marking something at layer 3, but the data is going through a switch, the switch may not be able to recognize that traffic based upon a layer 3 marking. It may be strictly a layer 2 switch. Plus, the layer 2 marking would not survive past the routing process. A layer 2 header is erased when it goes through a routing process. So any marking I create at layer 2 could not go all the way through the network. Now, even though some switches can read layer 3 markings, some cannot. So if I want to apply QoS to this to a particular type of traffic at layer 2, I may need to mark at layer 2. But knowing that that marking is going to be wiped out at the router, I may need to mark at layer 3 also, so that, as I said, that marking can be preserved as it passes its way through multiple routers. Okay? That way, the layer 3 header, including that marking, like diff-serve code pointer IP precedence, does survive router to router. Okay? Now, there are some more advanced switches, like multi-layer switches, that can do switching and routing. So they could recognize layer 2 and layer 3. But if a packet goes through a routing process, it's going to get a new layer 2 header. That's all there is to it. I can remap a layer 2 value, or I don't have to. It depends on the mission and what I'm trying to accomplish and where I'm trying to accomplish it. Since we are talking primarily about differentiated services code point, understand this is an IPv4 header. And the DSCP values are part of the TOS byte. Well, of course, we all know that a byte is 8 bits in size. Now, back in the day when IP was first created, they only set aside 3 bits for IP precedence. And instead of the least significant bits, they were the most significant bits. So the bits were the 128-bit, the 64-bit, and the 32-bit that were set aside for IP precedence. Well, with 3 bits, how many variations can we get? Well, in simple binary, that only gives us 8 variations. So you were able to have IP precedence values 0, 1, 2, 3, 4, 5, 6, and 7, making this a 1, a 2, and this a 4 in terms of IP precedence. 1, 2, 4 added up, 4 plus 2 plus 1 is 7, and 0 is a valid value, right? So that's why we had IP precedence, but 2 of those values were set aside. Values 6 and 7 were set aside for management traffic. So in terms of applying QoS to your corporate environment, you are only given 6 values to work with, 0, 1, 2, 3, 4, and 5. Okay? So around about Y2K, they decided that was not enough values to differentiate amongst the many types of traffic. So what they did was they created a new standard called the Differentiated Services Code Point, and they grabbed another 3 bits. Now, at that time, the other 5 bits were not used at all. This thing you see here on the right, notice the RFC for DSCP is 2474 and the RFC for ECN is 3168. That actually came along later. So there was 5 unused bits. Differentiated services code point came along and used an additional 3 bits, leaving the last 2 unused. And it was in a few years later that they came up with the idea of explicit congestion notification in RFC 3168 and found a use for those 2 bits. But again, we're talking about differentiated services code point. So how many variations can you get out of 6 bits as opposed to 3? Well, in binary logic, the number of values I can get is 64 different values. So if we place a value on the individual bits as 1, 2, 4, 8, 16, and 32, add those together and you get 63. And again, as 0 is a valid value, you have 64 possible values, 0 through 63. Okay? So DSCP is the toss byte in the IP header, and it's the 6 most significant bits of that value. Now, in order to comply with the previous standards of IP precedence, which still, if you were to send something through a network that did not recognize diff-serve code point and only recognized IP precedence, it would only look at the 3 most significant bits, not the 6 most significant bits. So to comply with the previous standard, they said we will still make anything that looks to a less advanced machine, like IP precedence 6 or 7, we will still make that, reserve that for management traffic. Okay, so if you notice, 3 more bits gives us 8 more values. So all of the IP precedence values are basically multiplied by 8. So what was IP precedence 5 is diff-serve code point 40. So IP precedence 5 looks like 101. Well, in DSCP, that's the 32-bit and the 8-bit. So in order to do that, they said, okay, anything that looks like IP precedence 6 times 8 is 48, on up should be reserved. So what would IP precedence 6 look like in terms of the toss byte? Well, in toss byte, in IP precedence, 1, 2, 4. So the 4 and the 2 would be high. Well, in diff-serve code point, that's the 32 and the 16. So that's where we get 48. But because I now have so many values, I can recognize more than 6 types of traffic. I can teach my network to recognize and delineate between more than 6 types of traffic and use these shortcuts of recognition. Look at these 6 bits, not at a whole bunch of criteria. So that's the idea with this. I have more granularity than just using the 3-bit IP precedence. So I can mark something diff-serve code point 0, or 1, or 2, or 3, or 4, or 5, all the way up till 47 if I'm abiding by the previous slide, or to 63 if I need some kind of management traffic to be recognized. So there's all these values. But the people who came up with the standard also came up with some shortcuts for how to recognize these values. And what they did was they come up with these things called class selectors and assured forwarding statements. So class selectors are right on the IP precedence boundary. So CS1 would look like IP precedence 1, and the last 3 bits would all be zeros. So if you look down this list of CS values, the last 3 bits are always zeros. Okay? So as I said, CS5 is the same thing as diff-serve code point 40 or IP precedence 5. Okay? So CS5 lives right on the IP precedence border, 101. But if I want to tell a machine to mark something CS5 or recognized it based on CS5, it will either mark or look at all 6 bits. But if I told it to do something based on IP precedence 5, it would only do the first 3 bits. right? So if I said recognize data based on IP precedence 5, all the data that looked like 101 anything, anything, anything would be recognized by that. It would take away my granularity. I wanted to recognize the difference between 101,001, 101,010, 101,011, 101,100. I wanted to recognize all 8 of the in-between values between CS5 and CS6. So that's why we are using differentiated services code point. These, again, are shortcut values. You can use them, you don't have to. But some of Cisco's tools automatically plug them in. So getting some idea of how they work is a good thing. So again, class selector. CS stands for class selector, and it lives right on the IP precedence line, but the last 3 bits are always zeros. EF, which is down here, is a very special marking. It stands for expedited forwarding. And it is always, in the binary, it is always 101110, which is decimal 46. A device that couldn't tell the difference, or that it was only doing IP precedence, would not be able to tell the difference between CS5 and EF. And that would typically be a bad thing, because EF is typically going to be voice and put in the priority queue. And I don't want to put a lot of things in the priority queue, okay? Because then we just have a large first in, first out priority queue. So I want this data to be recognized specifically. And then there are the AF values. Assured forwarding. The first 3 bits map to the IP precedence value. So in AF11, that first number refers to the first 3 bits and says this would look like IP precedence 1 in the first 3 bits. But what about the second 3 bits? The last 3 bits are used by things like weighted random early detect for default settings in terms of drop preference. And the higher the drop preference, the higher the number, the higher the drop preference in most weighted random early detect default mechanisms. Okay? So if it's a 3, it would have by default a higher drop preference than a 1. Now you can change the defaults, but that's a different course. Okay? And these AF values, you can only have an AF value whose second number is 1, 2, or 3. But they're only using the first 2 of the last 3 bits. Even though the first value of an AF value refers to the 3 most significant bits of the byte. The second value refers to the first 2 of the last 3 bits of the diffserv code point field. Okay? All of the bits are available, but if you want to recognize something other than something recognized with an AF value, you would just call it out by its binary value. You would just call it out by its value, like 35. So you wouldn't say AF 35, you just say DSCP 35. If you use certain tools in the Cisco world like Auto QoS, they love to classify and mark based on these values. So it would be valuable, it would behoove you to know how these values shake out or what they mean, okay? So as I said, the 35 is between AF41 and AF42. Does it exist? Yes, it does. So I could use DSCP 35 in conjunction with these things. I just can't use an AF shortcut to recognize it. So again, this is the map of how AF values work, okay? When it comes to AF values, the first number can only be a 1, 2, 3, or a 4. And if you'll notice, AF1 looks like IP precedence 1. AF2 looks like IP precedence 2, right? 1, 2, 4, right? In IP precedence, 1, 2, 4. And AF3 looks like IP precedence 3, and AF4 looks like IP precedence 4. And then when it comes to the second number, that has to do with the first 2 of the last 3. Okay? Now, these values can only be, there is no AF10, okay? There's only using 1, 2, or 3 for the second value. So this can be 0, 1, 1, 0, or 1, 1. Well, 0, 1, of course, is 1. 1, 0 is 2, and 1, 1 is 3. So the AF values, the first number here in AF11 means that the first 3 bits look like IP precedence 1, 0, 0, 1. And the first 2 of the second 3 also look like 1. That would have a low drop preference. But something that had a drop preference of AF13 going through something that's got weighted random early detect turn on would have a higher drop preference in that tool by default. Okay, so the first 3 bits match to the IP precedence. The last 3 have to do with drop preference, but it only uses the first 2 of the last 3. When you're taking an AF value, since they're never marking the 1 high, when you convert it to decimal, an AF value will always be an even number. It will always be an even number. That's why on that previous slide, you saw the value between the 34 and the 36. I said you could mark diff-serve code point 35. AF can't do that because it never uses the 1. I kind of like to do this. I like to work with showing people how these things map, okay? So what I'll do is I'll draw our toss byte. 1, 2, 3, 4, 5, 6, 7, 8 values, right? And in normal toss values, those would be normal binary values, right? 1, 2, 4, 8, 16, 32, 64, and 128. If you're doing weighted fair queuing or some type of queuing in a Cisco router, and you do show interface queuing, what it's going to tell you about the flows, among other things, it'll tell you the value of the toss byte. And it's going to use these values to tell you the value of the toss byte. From there, you can glean what the IP precedence or diff-serve code point value was. Now, if I'm doing straight diff-serve code point, remember, diff-serve code point does not use those 2 bits. So if I wanted to recognize diff-serve code point 35, not AF, right? Not an AF value or EF or a CS value. If I just wanted to recognize diff-serve code point 35, then it would be looking at those 6 bits, and those 6 bits would have values. Now, if I were to use AF values, these things would be a little different. In the AF values, those 3 are not used. Okay? So there's a 1 and 2 there, and a 1, 2, 4. So this is byte. This is DSCP straight up. This is AF and CS values, but I'm just going to say AF. And then finally, on a more primitive machine, if it were to recognize just IP precedence, it would see 4, 2, and 1. So you see, if something is IP precedence 4, well, that maps to class selector 4. IP precedence 4 would look like this in terms of the value for the entire byte. That's what the byte would look like. Okay? So that most significant bit, which in IP precedence is a 4, when it comes to DSCP, remember I said the class selectors live right on the IP precedence border? So that also is CS4. But the difference is with CS4, that's going to mandate that it looks like this. Okay? Whereas IP precedence 4 isn't looking at any of the rest of these bits, right? CS4 would say the first 6 bits must look like 100000. There would be no AF value for CS4. In DSCP, the bit that's high is the 32-bit. So IP precedence 4 looks the same as CS4, except CS4 pays attention to 3 more bits. CS4 looks exactly the same as DSCP 32. Okay? We've given a different value to the bits. The value of the entire byte is 128. So again, if you looked at this when in QoS statistics, he might say the toss value is 128. You can say to yourself, oh, I can convert that to looking at the bits, and I see that it's 128 for the byte, but it's DSCP 32 or CS4 or IP precedence 4. Let's take an AF value and see what that looks like in terms of the bits, okay? So I'm going to draw 1, 2, 3, 4, 5, 6, 7, 8. And we're going to take it for granted that we're not talking about those guys. And this line is kind of helpful to have in place. So what we're going to say is, if somebody says AF31, what do the bits look like? Well, remember, the left side of the equation has to look like 3. The right side has to look like a 1, but just in the first 2 bits. So that means that basically it's mandatory that that bit is a 0. Okay, well, how do I make the first portion look like a 3? Well, I can say 1, 2, 4 left to right, and that tells me that this would look like this. Even if I'm saying AF values, then this would be a 4, a 2, a 1, or diffserv values, right? This would be a 2 and a 1, and then this is an X, right, with AF values. So how do I get the 1 in the second part? Well, just like this. So AF31 looks like that. A 3 on the left side and a 1 on the right side, making sure we remember that not to use the last bit. Well, what does AF31 compute to if I wanted to recognize it just with diffserv code point instead of AF31? Well, now you would fill in the DSCP values. And in that case, what have we got that's high? The 2 is high, the 8 is high, and the 16 is high, right? So 16 plus 8 is 24 plus 2. So AF31 is exactly the same thing as DSCP 26. They are one and the same. So let's draw our values. And we're going to do this. And let's say AF 43. So if that's the case, then we've got to be a 3 on the right side and the 4 on the left side. Right? So it's going to look like this. What does that equal if I didn't want to use an AF value and I just wanted to say DSCP something? Well, the 32-bit is high, and the 4 and the 2-bit are high. So 32 plus 4 is 36, plus 2 is 38. Now I'm going to show you a little bit of a cheat. Now I'm going to do this because I think you're going to be able to watch this repeatedly, right? But since you can watch it over and over, okay, another way to convert these is to say 4 times 8 of the first value plus 3 times 2 of the second value. Sorry, that's a multiple. So if I said 4 times 8, that's 32, and 3 times 2 is 6. 32 plus 6 gives me 38. So that's how that works. Remember, there is no AF value for an odd numbered DSCP value. So if somebody tries a trick question on you and says, what's the AF value for DSCP 13, right? Your answer is there isn't one, because AF values do not use the 1 bit. So that's the idea. This is where that lives, there in the toss byte. Okay? In this case, they've said class map match any test, and they've said match IP DSCP 21. And just for fun, I've shown you what that is in the binary. Match IP DSCP EF. Well, that stands for 46. The EF stands for expedited forwarding. It has no numerical value. It's not hexadecimal notation. CS4, again, the last 3 bits have to be 0, and the first 3 bits have to look like IP precedence 4. So it comes out to DSCP 32. And then AF32, right, equals DSCP 28, which looks like 011100. You see, those first 3 bits look like 3, and the first 2 look like a 2, and we don't count the last one in that, right? I mean, in terms of the AF doesn't use the last bit. And what they've shown is that you can take these values and use them to mark traffic. So they've created a class map called test, and they've referred to it in a policy map and then said, change the marking. Any of those that I see, assuming I apply it on an interface, set it to DSCP 47, which would look like 101111. So remember, classification and marking, specifically DSCP, it's used to mark traffic so it's easier to classify it as it passes through the network. Layer 3 marking is created to be recognized by layer 3 capable devices. We might mark at layer 2 also so that switches, for example, can recognize marking and give us QoS based on layer 2 marking. But the layer 3 is persistent throughout our network. Just because we mark it one way at the edge doesn't mean we have to leave it that way. We can remark it if we want to. Remember, the class selector values, the CS values, live right on the IP precedence border. And the last 3 bits are always zeros. Expedited forwarding is usually used for voice. It's DSCP 46. A lot of voice devices mark it automatically. Assured forwarding values have that tricky kind of formula, right? The first 3 bits map to the IP precedence value. The last 3 are called the drop precedence values, and they are by default used by weighted random early detect tools that have default values built in, even though they can be changed. It only uses the first 2 of the last 3 bits, that assured forwarding value. Any other values you can just recognize by the 6-bit value, right? Like I said, like 35 or 13 or anything like that. You can recognize them all based on the actual value of the bits. Okay? And remember, in certain commands, they'll show you the value of the entire toss byte. So it might behoove you to, if you're doing some kind of a survey, to be able to convert the value of the toss byte to the DSCP value and say, oh, I see they've marked this thusly, right?